Our next presentation up is Christopher Dyck of COWI North America Limited.
Well, good afternoon, everyone. My name is Chris Dyck, and I hope you're all enjoying the conference so far. A lot of great talks here. This morning we discussed the impact of concrete bridge deck joints that aided a fatigue issue in the suspension bridges in Chile. So I'm going to switch gears a little bit here and talk again about concrete joints. This time it's going to be for the Northwest Arm Drive concrete bridges in Halifax, Nova Scotia. I'll discuss the background and condition of these bridges, the reason for the project, and then how we went about the engineering and the construction for the rehabilitation. So I performed this work I'll be discussing in the presentation while I was working as a structural engineer for Harborside Engineering Consultants. The bridge owner and client was Nova Scotia Department of Public Works. Whereas Halifax, we're, for those who don't know, we're hanging off the edge of Canada on the east coast there in the Atlantic Ocean. Connected to the mainland by a little isthmus to New Brunswick. The Northwest Arm Drive bridges were built in Halifax, Nova Scotia in '75. They consist of 5 55-foot girder spans, concrete girders, 6 girders per span, total length of 273 feet. So each bridge is supported on tall concrete hammerhead piers with heights up to 33 feet, and they're supported on spread footings. So context of the site, the bridges are located on Northwest Arm Drive in Halifax, and they travel above a former railway line, which is now a recreational trail, and also the outfall from First Chain Lake Drive, which is the backup water supply for the city of Halifax. This bridge sees AADT nearing 20,000 vehicles per day, and the twin bridge configuration you see here at the top of the aerial was very beneficial during construction, and I'll touch on that a few times. So here's the general overview prior to rehab. See the water supply beyond the bridges and the trail in the foreground. The bridge was over 40 years old when it made it to the Nova Scotia Capital Program for rehab. Over the years, Nova Scotia Public Works had regularly inspected the bridge and completed some repairs to the joints and girder ends. Unfortunately, the joints did not last long and continued to leak, and the typical practice of patching girders with bagged cementitious product has shown not to stand up to the test of time in our environment. Lots of salt from the ocean, lots of salt on the roads, and just lots of rainfall. Leaking joints, they allow salt-laden water to enter concrete girder ends and other structural components. So that deteriorates the concrete, accelerates corrosion of steel reinforcement, eventually leading to spalled concrete. This cycle just continues over and over, further advancing the deterioration. Prior to the capital project, inspections of the bridge were carried out to aid in estimating quantities for repairs, which is always a good idea. It was actually found that of the 120 girder ends on the 2 bridges, 110 of them required repair. So this ranged from minor to major, totaling 170 linear meters or about 600 feet of girder repair. When degradation was mapped throughout the bridge, it closely matched the flow of salt water, which you would expect. Many diaphragms also required repair, and most, if not all, 120 bearings were nearing the end of their service life. So major expense. The piers had multiple locations of cracking, spalling, and rust staining. The underside of the hammerhead pier caps had signs of corrosion, spalling and cracking as a result of leaking joints and poorly detailed drains that passed right down through. There were also a number of locations on the deck requiring surface repair. All 12 joints needed to be replaced, and the face of all barriers were spalled and deteriorated, requiring resurfacing. I'll discuss how the Department of Public Works approached the rehab, including what would have been done in a typical rehab and what was eventually selected for this construction project. First, the traditional method of rehab was considered. This was effectively replacing items in kind or like for like, and then repairing, patching, or strengthening other items such as girder end repairs, diaphragms, and deck ends. The trouble with that approach is historically these repairs have not lasted. As seen here, typical longevity of these repairs in our province range anywhere from 5 years to 20 for a very good repair. The reason for this depends on a multitude of factors, both prior and during construction as well as afterwards. Some of these include not selecting the best construction details or materials, workmanship, and maintenance problems afterwards. This would mean a fairly high cost to complete traditional repairs given their relatively short lifespan and the huge number that were required on this bridge. Compounded by the fact that additional funds would have to be spent in the near future for more repairs as those failed, leading to duplicated efforts, additional traffic delays, additional expenditures, plus poor public perception overall. Looking at all the issues with past practices for rehab, we knew there had to be a better way to achieve our goals for the Northwest Arm Drive Bridge. So taking a high-level look at what the objectives of rehabilitation were for this, listed here, long-lasting rehabilitation, if we're going to spend millions of dollars on a project, needs to be long-lasting, but it still also has to be cost-effective. Twin replacement bridges for this location, not including a detour bridge, was estimated to cost over $10 million. The project must address all concerns with the bridge condition, minimize traffic disruption, and ideally prevent future water damage. To alleviate maintenance issues, most new bridges in Nova Scotia now use integral or semi-integral abutments, which we heard about in the first talk. Continuous girders and decks, and improved materials and practices. A lot of box girders as well. Similar thought process of design for longevity was used as we approached the rehab of the Northwest Arm Drive bridges. It's obvious that the concrete degradation observed in this bridge was caused by the leaking joints. The rehabilitation approach chosen was to trial a new approach where all joints in the bridge are eliminated through design. All piers are integrated with the bridge girders and deck, and abutments are converted to semi-integral. While a similar concept using link slabs has been used in the past in Nova Scotia, this was the first application of a full pier integration in the province. So the original configuration has an expansion joint at the end of each span where it can leak onto girder ends, pier cap, and bearings, causing the deterioration I showed you earlier. Pier integration simply means removing the joints, deck ends, and diaphragms from each pier location, forming up the remaining void flush with each face of the pier, putting in some reinforcement and filling the void with concrete flush to the top of the deck. This completely removes the joints. At the abutments, it means converting from this, where the expansion joint is here and would leak onto girder ends and bearings, to this, where the abutments are configured as a semi-integral abutment, which moves the expansion and contraction to the bridge approach, where if it does leak, it does not easily reach the girder ends, beam, seat, or bearing. I don't know if this is a magical sliding abutment or not, but we'll hope for the best. What does this mean for the bridges? Well, full integration eliminates the need to jack and support girders during rehab, which is safer and easier for the contractor, especially when jacking against those damaged girder ends that we looked at there. A lot of unknowns. It eliminates the need to replace existing bridge bearings, reduces quantity of girder repairs, eliminates leaking joints, and gives also, this is a big one, improved surface smoothness. This bridge had a lot of bumps. The rideability was horrible over those joints. Some further advantages of the approach include simplicity of the system is a benefit to all parties involved. The repair process is faster as there are fewer steps with reduced effort to repair the girders. And while this sounds great and is conceptually simple, advanced analysis does need to take place to ensure that it's feasible. The joints, as you can imagine, are there for a reason in the original design. And now we're coming back 40 years later and fundamentally changing the structural behavior. So I will talk about that analysis that we did on the structure, the design, the tendering, and the construction. After designing the joint removals, we inspected the bridge and reviewed the available drawings and the geotech information, and realized that we would have to be sure through analysis that it would work before the department could proceed with this plan. Just couldn't recommend it to them otherwise. The main effect that we had to predict was how the bridge would behave when 5 single simple spans of about 16 meters each suddenly become one continuous span over 83 meters long. I think it's 270 feet. So what does this do to a bridge when you suddenly force it to go from simple to continuous? As many of us are aware, on the left I'm showing the behavior of a simple span. The shear is balanced and the bending is uniform and goes from essentially 0 at the edges of each beam, rises to a maximum in the center of the span. And on the right, I show you the behavior immediately after integration to continuous. You can see that the shear is no longer uniform. The pier has attracted additional shear as the peaks are higher. Also, the structure is no longer as free to rotate at the support locations, so this also attracts bending moments to the piers. So after integration, the piers were suddenly subjected to higher vertical loads than they were originally designed for, and the top of the deck started to see stretching from bending that it was not designed for. To capture the key effects going on in the bridge, we developed beam and shell finite element models, and we looked at cracked and uncracked situations as concrete behaves in a different manner depending on the cracking condition. We also developed shell models of the piers and footings to capture effects like two-way bending in the piers, differences in the settlement of the various soils under the bridge after integrating the structure to continuous, and pressure under the footings with the increased loads. So here's the base level finite element model with the deck shells turned off so you can clearly see the girders, pier models, and support conditions. This bridge is also on a curve, so that added a little bit of complexity. Going back to the diagrams I showed earlier, simple versus continuous behavior, this is the model of the bridge behavior under its own dead load. You see the additional bending at the piers. In this particular program, the convention in the model is sagging of the structure is shown as orange or red, pointing up above the girders, and hogging is shown as yellow and green, pointing down below the girders at the piers. We changed the abutments to semi-integral so they were free to slide to allow the much larger temperature movements to be taken up there. Your thermal null point has now moved to the center of the bridge, not in the center of each span. Similar at the abutments to the simply supported beam case I showed you earlier without any bending attracted there. Here we see an envelope of the results for 2 design trucks running as moving loads on the bridge in the 2 lanes. The trucks are positioned at multiple locations on the structure, and we're seeing the maximum and minimum bending moments in the diagram that were then added to the dead load of the concrete and increased by the appropriate factors based on the Canadian Bridge Code S6. You can see here again the increased bending moment at the piers on the continuous model. Some of our analysis cases looked at the compounding effects on the structure of wind loading, particularly because the piers are tall, up to 33 feet. And this area is relatively open to winds and can be exposed to hurricane force winds in any given year. The diagram shows just one case of many wind load cases where the wind was applied as a partial quarter point loading. You can see significant bending occurring in the piers to resist this sideways loading. One case we were also really concerned about was what would happen when we increased the pier loading and one of the piers was on different soil than the adjacent pier or abutment. This diagram shows a case where we forced the first pier to sink into the soils while leaving the north abutment on firm soil, as is the case from the geotech information. And you can see the increase in bending that occurred over the first pier and was transferred into the second span. Fortunately, in our case, the overall impact of this mechanism was small on the structure and it didn't prevent us from making the bridge continuous. We were able to get around it with strengthening. With the results of the analysis, we put in additional strengthening measures at the pier hammerheads and in the new deck to allow them to avoid significant cracking under the new loads, and we took account of this in the analysis. So the conclusion of all the analysis was that the bridge had just enough capacity following the integration steps to resist the additional loading it was now expected to carry, taking into consideration our strengthening. Next, we'll just discuss a few of the tender considerations for the project. This type of approach was new to Nova Scotia, and as we heard the last speaker suggest, doing trial runs and paying a little more attention is good when something's new. So we decided to go the route of extra detail in the design package to avoid confusion and to inform the contractors who bid how to do the new procedures. Extra detail also removes some of the mystery of the job and made it easier to bid more accurately. So a little more effort on the design and documentation. One example of this was in detailing exactly how much of each girder needed to be repaired and by what procedure. All procedures were diagrammatically outlined and also had a set of notes describing every step. So here are just one of the tables of girder repairs that were required outside of the new pier integration areas. We avoided extensive girder end repairs by enclosing the majority of the damaged ends in the new pier concrete pours, but we couldn't take those pier pours too far into the span. It just wouldn't be economical or reasonable, so then we still had some minimal girder repairs beyond that. This is one of 4 procedures for repairing girder ends that was developed and referenced in the table that I just showed you. Construction phase of this project was interesting and different. I'm going to show you some of the steps that were followed by using pictures taken in the field. Easier on the eyes. The first step in the construction was to divert traffic off the bridge that was being rehabilitated. Traffic was maintained as one lane in each direction on the opposing bridge that was not undergoing work. That was a huge advantage. The successful contractor chose to remove concrete using hydrodemolition. Hydrodemolition involves shooting a high-pressure water jet at the concrete with a pressure up to 20,000 psi and disintegrating the concrete into small pieces. On the right, you can see the hydrodemolition machine shrouded to remove barrier concrete to protect the vehicles on the other bridge from the high-pressure jet. I mean, they were only 6 feet away. Jackhammers were also used for small areas and areas where it wasn't practical to set up the hydrodemolition machine. We're right near that water supply for the city of Halifax, so all wastewater had to be carefully collected and filtered to avoid contamination and environmental issues. The water jet broke up the concrete and left the reinforcing steel clean and ready to be incorporated in the new concrete pours. Worked great. Back of the barriers were in good condition, but the front exposed to road salts needed to be repaired. So we removed concrete to an inch below existing reinforcing and then formed and poured new barrier faces using a 5,000 psi ready-mix concrete. This is just following through the barrier refacing process and then the completion of that. So the bridges were built with an exposed concrete deck, and there were areas of delamination, so we did traditional partial and through thickness deck repairs as part of the rehab, all that done with hydrodemolition. Piers and abutments had cracking that needed to be repaired, so we used pressure injection of epoxy resin. We set a threshold of crack size per the Canadian Bridge Code for salt-exposed structures of 0.25 millimeters, and had the contractor fill the cracks starting from the largest cracks and winnowing down to the smallest unacceptable cracks within the quantities we had on the project. This will help to extend the life of the substructures even more, especially now that the water has been diverted through joint removal. Epoxy creates a structural bond. As described earlier, the piers were opened up, joints removed, diaphragms removed, additional shear and bending reinforcing steel was added, and the pier hammerheads were used as the bottom of our formwork. We closed in the sides and filled in the pier to top a deck with new concrete. This shows the hydrodemolition being used to remove the deck and diaphragm concrete and expose the reinforcing steel, right down to the pier cap. Scaffolding was used for work platforms to support the operations on the pier integrations. The existing longitudinal deck reinforcing was maintained and just bent temporarily out of the way to allow adding vertical epoxy doweled steel to the existing pier hammerhead to give a connection to the new concrete. Existing precessing strands were located in the ends of the existing girders using radar, and holes were drilled through the ends of the girders to provide locations to pass steel bars through the girders to provide necessary shear connections to the new concrete. These photos show the new vertical and shear reinforcing that was added to the integration areas. Vertical steel bars are glued into the existing hammerhead concrete using epoxy. Bottom picture shows additional steel that was added to control cracking from those new bending moments I was talking about earlier. And that's the concrete pour underway at the top left and completed at the bottom for the pier integration. These are the two types of pier integrations that we designed. The one on the left is for areas where the girder end damage was a little bit less extensive. The one on the right was extended out to encompass more extensive girder end damage. These were applied throughout the bridge as required. Temperature changes caused the new bridge to expand and contract in a concentrated fashion. The piers flex slightly to accommodate some of the movement, but the majority is now transferred to the abutments, so we had to allow for this movement by adding 2 sliding bearings and converting the abutments to semi-integral. One of them was fixed before. We eliminated the joints that were causing so much damage to the girders below by adding approach slabs and moving the joints off the bridge. And I don't know if this detail was picked up in the earlier study or not, but that's the detail that we used. Most of the concrete was removed by chipping at the abutments, as it was difficult to get the hydrodemolition machine positioned there. With the approach fill removed, it was just an order of operations on the contractor's part, so they used jackhammers. At the north abutment, the former fixed bearing had to be removed and a free bearing installed. This required jacking of the girders and breaking out of the abutment beam seat to allow us to build a new bearing support. Jacking brackets were attached to the front of the abutment, and the girders were raised off those using bottle jacks. And here's the new steel being placed and the new concrete being poured for the semi-integral abutments. These are the approach slabs going in to move the joints off the bridge and try to get that smooth riding transition, which these didn't have before. It just had an expansion joint. The girder end repairs outside of the integration areas. Clamshell form was developed that had a hinge in one corner and could be reused for multiple repairs. They used it throughout the bridge. Here it is in place, showing the bird's mouth concrete ports for supply of concrete and venting of the form. The new concrete jackets are held in place with steel reinforcing that is drilled and glued into the girder, webs away from the pre-stretching strands with epoxy. Concrete for the girder repairs was a bag mix that had an integral corrosion inhibitor and small size aggregate for flow. Sacrificial anodes were also attached to the reinforcing steel within the repairs at about 2-foot centers, slightly less, to increase the longevity of the repair before the onset of future corrosion. Don't want to go back there anytime soon. Here's one of the locations where the shear stirrups in the girder were broken. They were lost from corrosion. So we wrapped the repair area with sheets of fiber reinforced polymer to give it more strength. And then to summarize, I'm going to show a few slides of before and after for the various areas that were rehabilitated. Here we have severe area of degradation before at the top of the slide. And then on the bottom, after the piers integrated and girder ends are repaired and wrapped. For the pier repair, original hammerhead surface was very corroded. Drains went right through. After repair, we removed those drains, and also there's no longer a source of water. So the concrete's been cleaned up and reinstated with all the cracks sealed up. The joint that was previously present at the abutments led to a lot of water damage. So on the bottom, you can see the new semi-integral configuration, and we actually designed those cutouts there for future jacking. And the diaphragms are designed for that as well. The barrier transition, and also one of the requirements was the design needed to account for the additional bending and shear resulting from adding an asphalt driving surface. That was one of the nice to haves. So the bridge obviously never had that before. It was exposed deck. So we designed for that, and now there's an asphalt wearing surface and no joints on the bridge at all. This was 4 years ago. I went out a couple weeks ago just to see how things are doing. Repairs are showing no signs of deterioration at all. Bridges are shedding water effectively, and the girders and piers are being protected from the road salts as we intended. Here's one of the extended pier integrations, still in very good condition. And this is a location that was formerly showing that worst degradation with just everything crumbling and exposed rebar everywhere. So changing from simple spans to continuous with the additional reinforcing measures is clearly well tolerated by this structure. This procedure is broadly applicable, and it's expected that this approach is going to be used more in the future. I've heard Nova Scotia Public Works talking about it for at least 2 other bridges. But the applications need to be chosen carefully for several reasons. Without the ability to close the structure by providing a suitable detour or crossovers, the logistics get much more complex with traffic in the work zone. Converting from simple span to continuous does not favor having a longitudinal bridge joint, so lane by lane is not great. Design effort is more extensive and complex than traditional approaches, as you'd expect. Low bid for construction was $2.1 million in Canadian dollars 4 years ago for both of the bridges. It's expected to last up to 40 years or beyond, getting the water out of there. Traditional end girder and joint repair would need to be repeated about 4 times in the time frame that we're looking at for this one, for an older concrete bridge. We estimated it at the time at about $1.25 million per rehab job. So we would have been looking at up to $5 million for traditional approaches in today's dollars, or 2017 dollars, during the remaining life of the bridge. So the upfront cost is higher, but there are significant life cycle cost savings afforded by this procedure, and there's significantly less impact on the public over the remaining life of the structure, as there's only need to detour traffic once. But this won't work everywhere, as I described, so you have to pick and choose. All right, so thanks for your attention and invite your questions. Yeah, we did look at it, but we didn't think it was necessary. No, especially once you fill it, once you seal with epoxy and then you get the water away. It's not, nothing going on there. Well, we did model with the curvature.
Okay.
Yeah, so, yeah. We had the geotech from the original construction, so we used those soil properties. Yeah, and actually it's interesting you asked that because in the original configuration was simply supported spans. You're actually rotating above the top, right? But now we've changed it continuous, so now you change that rotation, you get the pin at the bottom. So now you're taking your footing and you're trying to lift it. So there was one small corner where the stresses, we think, might have spalled the corner of the footing off, but we're not too concerned about that. Yeah, we modeled it with like modulus subgrade reaction, converted that to springs. Yeah, did the full meal deal. It helped a lot. Yeah.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.